Has this ever happened to you? You're walking around on a hot summer day, and the door just won't open. And not even help from your strongest friends will help the door come open. I wonder if our friends from Conair can help. Oh, what good news! It seems as though the Super Cool Group has developed a solution that will save our poor friend. Hi, we're the Super Cool Group, and over the course of the semester, we worked with Conair to develop a solution that eliminates aluminum door frame expansion due to the bimetal effect. The bimetal effect seen in Conair's doors mimics the behavior of composite materials when they thermally expand. Composite materials might have two different coefficients of thermal expansion, which will cause one material to expand more than the other, which will lead to bowing. In the context of a door frame, you see a temperature gradient across the outside surface and inside surface. The outside hotter surface is exposed to thermal radiation and will therefore expand more than the inside surface, which is exposed to forced cooling. As a consequence, Conair doors might jam during hot summer months where that temperature gradient can get up to 100 degrees Fahrenheit. Thus, for our proposed solution, we wanted to mitigate or eliminate the bimetal effect in Conair's doors. There are three main things that went into performing this project. Our goal was to either reduce the temperature difference between the surfaces to match their deformation rates, to provide structural support to the inside of the frame so that even if there is a high temperature difference, we're not seeing the same level of deformation or jamming. And our main goal was to use COMSOL, an advanced multi-physics package, to create an application that models heat transfer in Conair 500T series door frames, and then use that as our model. Specific specifications that went into designing this product include mitigating or eliminating deflection and expansion from the bimetal effect and requisite thermal and mechanical strains. We wanted to maintain the exterior profile and coloration for their commercial door applications so that companies that already trust Conair are able to continue to use their products with superior performance. Additionally, we wanted to ensure that this does not negatively affect the thermal efficiency of the aluminum urethane thermal break. And we needed to ensure that we had minimal material and manufacturing costs for this door frame. The efficacy of our models in actually eliminating this effect are based on the results of an experiment performed by Conair where they used heat lamps to emulate the effects you might see in the summer in places like Arizona or New Mexico. Only the bottom rail of the door was used in this experiment. We find an experimental linear expansion of 0.06 inches and an experimental linear deflection of 0.038 inches.
First, a simulation has been run on the base unmodified door frame, and the resulting linear expansion and deflection values closely match those of the physical experiment run by Conair. The simulated boundary conditions are therefore well validated and are used to verify our design concepts.
This is where we started our project, with brainstorming. We have two main classifications of concept type. There are concepts which attempt to structurally prevent expansion and deflection, such as the bracing, thickened outermost extrusion, and additional extrusion with bracing. Then there are solutions which attempt to manipulate how heat transfer occurs through the extrusions, such as the cap on the outside of the door and fins to dissipate heat. Ultimately, some of our brainstormed concepts were not viable as they would too greatly change the aesthetic layout of the door, namely the concept which proposes machining holes on the inside extrusion for convective cooling.
This is the drawing for the cap design to show the dimensions. The idea behind the cap is to increase the amount of heat the frame undergoes by adding another layer to decrease the overall effect of the bimetallic effect. The outermost extrusion can be made from a light metal, for our experiment aluminum 6063 T5. Then the piece in contact with the frame and cap is made of ABS to decrease the amount of heat transfer to the door frame since it has a low thermal conductivity.
So here we have the simulation results from the cap. As you can see here, the cap was very effective at reducing the overall deflection of the door with a minor change to the amount of linear expansion. From all the concepts we've shown, the most promising concepts we have are the cap, the additional extra thickness, and the fins on the inside of the door due to their effectiveness in reducing deflection and their overall minimal cost or ability to be retrofittable. From these choices, we then modified and combined some of these concepts in order to find out if they would be more effective in any way. For this concept, we tried removing the ABS plate in the middle of the cap to see if it was necessary as a thermal insulator, and we found that the results were almost identical to the cap with the ABS plate. From our modified concepts, we found that all solutions were strictly dominated by the cap's effectiveness, but the cap with the ABS clips could be seen as a cheaper alternative to just the cap by itself. From all our solutions, we chose the cap with the ABS clips due to none of the combined solutions being more effective than the cap by itself, and the cap with the ABS clips just being a cheaper alternative to the cap. It is worth noting that if cost is the most important factor, the thickened wall solutions might be more cost efficient, but less efficient at reducing. In conclusion, all of our concepts focus largely on reducing the temperature gradient across the door frame or adding structural support as the most effective ways to reduce deflection. The expansion was caused mostly by the aluminum's coefficient of thermal expansion and was largely unchangeable unless a different material will be chosen for the door frame. The cap with the ABS clips was chosen as our solution due to its deflection reduction amount and the decreased cost compared to the normal cap. Any future testing could be able to run experiments with these concepts to confirm our simulation results, and we can improve the simulation model by changing our convection parameters and adding fluid domains.